So good morning, everyone. So we will our discussion on concluding chapters of electrodynamics. So yesterday we discussed something about uh, that we started discussion how uh, we can write Maxwell's equation in terms of the scalar and vector potential. Okay, so this is again what we did towards the end of the class. So we could one can write the Maxwell's equation, the four Maxwell's equation, into two Maxwell's equation, which are a inhomogeneous differential equation. One in the form of the scalar potential phi, and the other one in terms of the vector potential A, which are now separated using the Lorentz gauge condition, which is given by this. Now, why we want to work with this kind of formulation? So when the so far what we have discussed is the electric field or magnetic field that is produced due to a stationary charge or a steady state current. And then we obtained this electromagnetic equations, Maxwell's equation. But then we, without bothering too much about the source of this electromagnetic field, so we just looked at how this electromagnetic wave propagates in different medium. So what happens when it encounters to different kind of medium? So there will be reflection, there will be refraction, there will be transmission. So all these things will happen. So which leads to the part of optics. Then how the wave propagates in vacuum, how the communication works. Okay, so this is all part of, without really considering about what is the nature of the source itself, because we know that according to the Maxwell's equation, so the electromagnetic field can propagate even without in presence of a source or any charge density, so to say. But of course, when we look at how this electromagnetic field originated in the beginning, so there has to be some a motion of the charge. So there should be a variation of the charge distribution that gives rise to a like a oscillating electric field or a oscillating current. So not a steady state current, but a current which also it may oscillate, but it may vary as a function of time. So that will give rise to a time dependent magnetic field. But if we consider that, okay, so if we say, let's say we have a time dependent charge distribution and a time dependent current distribution. If we assume that and try to calculate electric field and magnetic field, we will have we have to solve very complicated differential equation. So just to give you one example, so if I take let's say we start with the third Maxwell's equation. So curl of B is equal to minus del B by del T. And we take the curl of both sides. So we have minus the curl of T. Okay, so this will be equal to del of del dot E minus del square E. That is equal to del by del T into, in place of curl of V. So I will use the fourth Maxwell's equation, the mu naught J plus 1 by epsilon naught mu naught Oh, sorry, it's not. So this is epsilon naught mu naught del E by del T. Okay, so now if I write the wave equation, so assuming, let's say, the del dot E is 0, or even if you want to put del dot E, there will be this rho by epsilon naught term will be there. Then if I just put this del square E, like the familiar wave equation that you know of, so those terms I will put it in one on the left hand side. So it would be plus mu naught epsilon naught del square E by del T square equal to minus del J by del T. So there is a mu naught term, and then there is also this del of rho by epsilon. So even if I say there is no gradient in rho, let's say, so this term I can still say 0, but I have a time varying current density, so which is on the right hand side. And solving this kind of inhomogeneous equation is very, differential equation is very, very difficult. So this is why instead of solving the electric and magnetic field directly, so what we do is we solve for the electric potential or the scalar potential and the vector potential. First, we find a solution for that, and then from those scalar potential and vector potential, we calculate what is E and B. Okay, so if we use these differential equations now, and so we calculate phi and A. And how do we calculate E and B from this phi and A? So it is always, so B will be simply as curl of A, and your electric field will be minus gradient of phi minus del A by del T. So this is always, so what we do in this today's class is basically we have to find out a solution for phi and A for different conditions, and then just use this. Once you find A and phi, so you can then calculate B and E corresponding to whatever charge configuration you are considering. Now again, here we take a help to find a solution. So we take a help from mathematics known as a Green's function formalism. So this is Green's function formalism to find a solution for phi and A. So the basic the solution for this kind of inhomogeneous differential equation is simply, so I will just write down the mathematical expression in general, and then we will extend it to the scalar and vector potential. So the general Green's function formalism is like you have a function del square u r t minus 1 t square del square u by del t square, so is equal to function of f of r and t. Okay? And this f of rt is what we call as a source term. Okay, so this describes a general wave that is propagating at a velocity. So this is a wave. So this represents a wave propagating at a velocity. So this velocity is a phase velocity, v. So here we want to find out what is qrt, which is given by, so minus 1 by 4 pi 1 by r minus r prime function of r, t, r, and dv prime. So what is this r prime and r here? So we want to find out the electric and magnetic field, or let's say the potential, scalar and vector potential at point P, which is defined by a position vector r. But what is the field due to the source? So we have a source which contains, let's say, charge or your current density. It can have your charge or current density. Now, which has a time dependence. So this charge density and current density, they can vary as a function of time, which is, let's say, situated at a position vector r prime with respect to your origin, and this vector r, so is your r minus r prime, and the modulus, the distance is the modulus of that. And so within this volume, so this is, let's say, we say take a small volume dv prime here, and whatever changes that is happening within this small volume element, so that information does not or takes some time. So depending on what is the phase velocity of the wave, okay, so depending on that, so it will take that much time to reach this point P. So therefore, at this instant, so if we want to calculate the field at point P at this distance, so we should find out what was the charge distribution or current distribution within this volume element at a earlier time, tr, okay, so which is this tr here in this integrand. So tr is the retarded time. So what is the charge or the current charge density or current density, how it is I in this volume element at the time tr, which is given by the current time t minus the time divided by the velocity, okay, or this is t minus r by vp. So in case of electromagnetic wave, so this phase velocity will be equal to your velocity of light, or simply c. So this is the most important concept, and this, due to this effect, so the electric field and magnetic field all will be modified, which will be different from your expression for Coulomb's law or the Biot-Savart law that we saw earlier. So basically, we have to now, when you look at these equations that we wrote for scalar potential and vector potential, so it exactly looks like how the Green's function formalism will work in this case easily, because we can write it in terms of this.
The solution is important, or we have to remember the result only? Means the whole formalism is important to understand.
Whole formalism is so I am just telling, let's say, the basic things that you need to understand how you can solve this problem in different situations. So in the book, you will find it has been solved for different situations. So when a charged particle has certain time dependence, it has, let's say, moving at a uniform velocity, it has a acceleration, okay, so under different condition, so this phi and a, the expression or the solution will change.
Okay,
Okay.
so that means we have to understand the whole formalism so that we can apply it
Yes.
to different
Apply.
conditions.
Yes, yes, yes.
Okay, okay,
Mm.
okay.
Yes.
Thank you, sir.
So we have this phi equation in phi and a. So this equation is not going to change. Okay, so only, so the dependence, how it depends on time, how it depends. So the like the phi, the dependence, the this is phi and a. So these are all functions of r prime and in this coordinate frame. Okay, so we are this phi and a, so all are defined with respect to this r prime, this coordinate frame. But what you want to find is the electric field and magnetic field in the r coordinate. Okay, so this is where you have to be careful. Okay, or let's say, so the charge distribution, no, sorry, so the charge distribution rho and j, so the charge density rho and the current density j, so they are in the always in the coordinate with respect to r prime. So that means r prime means it has x prime, y prime and z prime, and here this coordinate is defined by x, y, z. So what you are always interested in, so something that is changing in x prime, y prime and z prime, so how that translates and affects your electric or the potential or scalar potential and vector potential and eventually electric and magnetic field in at xyz. So this is where you have to be very careful when performing these or solving these equations, differential equation. Uh, so with so now since we have written down this potential term, so now we can say what will be the solution for phi and a. So we can say, so phi at r t will be, so this is always why while doing this kind of solving this kind of equation, so you have to always write the correct the coordinates. Okay, so x, y, z, whether it is r or r prime, whether it is t or t prime, so this you have to be very careful when you are writing. So we are solving for the potential at point p, so which is given by the position vector r at time t, and so using the Green's function formalism, so the solution will be 1 by r minus r prime rho r prime and tr. Okay, so this is at a retarded time dv prime. So what is tr here? So tr here simply your t minus r prime divided by c. So this is for electromagnetic phase. So the phase velocity here is the c velocity. This is what we need to. This is the solution. Okay. And similarly, we can write a solution for a vector potential, which will be given by this constant term mu naught by 4 pi and r minus r prime. This is the modulus. Then there will be the current density J at r prime and at a retarded time tr. So these potentials therefore are known as retarded potentials because they depend on this retarded time tr, so this function of rho and j at time tr, which is a retarded time. So these two potentials are normally known as a retarded potential as well. Okay, so we can, so if you actually compare it with a static charge distribution, so let's say there is no time dependence of the charge distribution. Okay, so rho does not have any time dependence, so it is always the same, and j also does not have a, like, it does not vary. So the phi in that case, so if so rho and j have no time dependence, so in that case your phi rt so is simply would look like, so we have the same situation, only we are saying this rho is not a function of time. So in that case, it will be simply rho r prime dv prime, because there is no time dependence. So tr does not make any sense. Rho r prime is always the same, and therefore the scalar potential will be like that, and vector potential exactly. So you don't have any time dependence. So when you look at compare these two equations, for example, this one and this one, so they look exactly similar, right? In terms of expression. Okay, only thing is in the bracket, so you have TR dependence. But this is important because this brings a very new insight into what is the nature of electric and magnetic field will be at point. Although mathematically they look pretty similar. Okay, so but this let's say if you say this is my phi rt, which looks like this, and in case of a static charge distribution, then charge density, so the scalar potential would be like that. So can I just write my electric field at point P simply like using just the Coulomb's law, where can we write it like r minus r prime divided by r minus r prime cube into rho r prime tr tv prime. Can we write it like that? No, we cannot just simply write. So this is just your simply the Coulomb's law. Okay, so this the expression for electric field that we get in case of a static charge distribution. So this is your Coulomb's law, but this is not true when we say this rho has a time dependence. Okay, so what will be the form of this electric field and then magnetic field? So let's just look at the electric field form. So what you can see also, where you can also verify, so since we are writing the solution using the Green's function formalism, so I say phi rt is a solution, art is a solution for these inhomogeneous equation which we wrote here. Okay, so this equations that we wrote here. So that means if I now substitute the solution here, so I should be able to, so this equation I should be able to solve basically. So what you can do is, so that is given in example in the book. So you just substitute the solution that we wrote, try to calculate these left hand side and right hand side and see whether they are the same or not. So that you convince yourself, okay, what the solution that we are writing is correct. Okay, so now let's look at how the electric field and magnetic field would look like for this potential. So here you have to be very careful. Okay, so we know that in order to find the electric field, so we have to find this gradient of phi minus del A by del T. So we have a solution for phi and A. So phi is given here, A is given here. So we have to take the gradient of this function and time derivative of this function. But remember, the gradient what we are taking is gradient we are taking in terms of the x, y, z. Okay, so the gradient that we are writing here, it is del by del x, del by del y, del by z. But whatever inside the integrand, this is r prime, it is a function of r prime and t prime, which is a function of x prime, y prime, z prime, and tr. Okay, so this is why, so when you are doing finding out the gradient, you have to be very careful how you are doing it. Whether you are differentiating with respect to, so for example, if this is just, if I take a function, so I'm just saying function, it is a x prime, y prime, z prime, okay, and I am taking a partial derivative with respect to x, so this will be 0, because x prime and x, they are totally independent of each other. So therefore, when you are doing this calculations, finding out the gradient or doing a differentiation or integration, so you have to be careful what are the variables and whether you can perform those or not. Uh, so the expression or the solution for electric field, so by substituting the value of phi and a, what we will get is minus 1 by 4 pi epsilon naught del gradient of 1 by r minus r prime into rho plus 1 by r minus r prime into gradient of rho dv prime, and we have to find out also del a by del t. So here we are just writing this del a by del t, which is nothing but del j by del t, but here j is a function of r prime and tr dv prime. Okay, so this is just simply we are substituting or writing this gradient of phi. So gradient of phi, I'm just writing the gradient of rho. So we have two functions. Okay, so there is 1 by r minus r factorial, and then there is r prime and tr. So I'm just taking a gradient of this, the gradient of this term first and multiplied by rho, then plus. So simply I'm doing the differentiation like you do normally. Okay, if you have a product of two functions. Okay, now you can write all these terms exclusively. So you can calculate what is the gradient of 1 by r minus r prime, the gradient of rho. So this is again you just do it yourself, and what you will find eventually is 1 by 4 pi epsilon naught rho r prime er. So these are all this differentiation you have done in mathematical physics. Also, partially you must have done in electrostatics as well. So this is equal to r minus r prime plus rho dot. So I am writing a rho dot, which means this is a partial derivative with respect to time t, r minus r prime modulus square, then multiplied. So this is also multiplied by r minus r prime. There is a term which is minus 1 by c square j dot. This is a r prime tr divided by r minus r prime, and this is how the expression for electric field looks like when the charge density has a time frequency. So the first term is what you see is very similar to your, this is the Coulomb term. So similar to your, what you expect from Coulomb's law. The second and third term, as it indicates, so what is rho dot? So rho dot is nothing but del rho by del t. So similarly, j dot is here del j by del t. So this, the time dependence, because of the time dependence, so you have some extra terms in the electric field which is different from your Coulomb term, and these are known as, so these extra terms are known as the radiation field. So what is interesting about these two terms, so if you look at only the, so the first term is simply like 1 by r square dependence. Okay, the second and third term, they are this, so the radiation field, so it depends on like 1 r minus r prime, okay, or which is simply 1 by r. We can just write like that. So this is a radiation field varies as inversely proportional to r. Uh, and why we are calling it a radiation field? Because this is the field, electromagnetic field, which actually we can observe far away from the charge distribution. Because the according to the Coulomb law, so the electric field varies as, if it is varies as 1 by r square, so it will decrease very quickly because it is a 1 by r square dependent. But the other two, because they have 1 by r dependence, so they will decrease slowly compared to the first term, and they will actually dominate the electric field, how it should look like at a far away distance from your sources. And this is why, which are responsible for basically this electromagnetic radiation, and we call them as electromagnetic radiation. So similar expression you can also get for uh, magnetic field as well. So you will also have a radiation field corresponding to the magnetic field when you write, when you calculate P, you have to calculate this curl of A, okay, and you will find out what is the expression for that, which is also different from the your Biot-Savart law. So you will also have similar two extra terms here. Sorry, one extra term here. So one terms just exactly like what you expect from Biot-Savart law, and one extra term which depends gives a time dependence of your current density, and that also varies as 1 by r. So just exactly the radiation field, and that corresponds to the electromagnetic radiation. Okay, so the next in this unit, so basically what has been done is, as I said, so you have to write this Maxwell's equation in terms of phi and a. Then you write it for different situations where the charged particle has a uniform velocity, or it has a some acceleration, and that leads to different kinds of radiation. So another aspect of here is like you also have something, a dipole radiation, which is normally used quite a lot in applications. So there is a electric dipole radiation, and there is also a magnetic dipole radiation. So both are related to a time dependence of your dipole moment. So P, which is a function of T, and here your magnetic moment, magnetic dipole moment, which is a function of T. So normally, for simplistic case, so you assume this is cos omega t. So this will be also m naught cos omega t. And what is P naught? So P naught is equal to the charge distribution. So if it is, so if I say this is plus q, this is minus q, separated by a distance d. So this is given by q into d, and the m naught will be given by the charge into the area. So if I take a circular kind of, so this is my charge, and this is has a radius r. So this will be simply q into pi r square. Okay, the maximum magnetic moment. So this oscillates as a function of time, which has this kind of dependence, and this gives rise to also a special kind of electric potential. Again, you calculate the potential due to this dipole, electric and magnetic dipole, and then calculate what is the E and B field, and this corresponds to a dipole, electric dipole and magnetic dipole radiation, which is quite used quite a lot uh, in engineering application. For example, when we talk of a, if you want to send a signal, okay, so you have to create an antenna, design an antenna, special antenna, so which will be able to based on either electric dipole or a magnetic dipole, and you apply alternating electric field so that this dipole basically oscillates with some time dependence. Okay, so this is here we are saying it is a cosine like function. So due to this variation, so you will have a radiation which propagates along certain direction. Okay, so this is how you can then transfer your so which will carry certain energy and power. So you can then transfer this power from one point to another point. So the example of this is it's like in your microwave that you use at home. So how the microwave is delivered to where the food is. So it is through, so you generate using a, a special kind of a magnet or a dipole. Okay, so this is known as a magneton. So you apply a AC current, and that produces this oscillating dipole field, which then produces a microwave radiation. Now, the microwave radiation is not like if you just allow it like that, so it will spread in all directions. So in your microwave, what they do is you use as a fiber optic, like a cable. Okay, that cable transmits that power from the source where it is generated to where you have kept the chamber where you keep the food to heat up. Okay, so this is a simple way which you have seen. I hope you have seen in your everyone has used. So similarly, this kind of radiation also is used for a radio communication. So you tune into a particular frequency and listen to a song or any news in radio, or even earlier times it was due to TV, all due to this dipole antenna we used to have. If those who remember, so we used to have an antenna, but nowadays, again, you have this dish antenna, which is a different design, okay, which is capturing, of course, it is capturing a part of electromagnetic radiation, but it is not any arbitrary radiation that you have, but that is coming from a particular satellite that you are collecting. Okay, so now we will move on to quickly the last unit, that is the spatial theory of relativity. So here in this chapter, so what you have is basically it is in a way it would appear there is no relation between electrodynamics and special theory of relativity. So special theory of relativity that was proposed by Einstein is about how you transform a particular physical principle from one set of reference points or a one frame of reference to another frame of reference. So what he said is like all the physical principles should remain invariant if it is observed from a frame of reference uh, which is not moving, and another frame of reference which is moving at a constant speed with respect to this rest frame. So all the physical principles should remain unchanged. That is also correct, which was earlier kind of people knew about it. And the second postulate, which is most important, is that all this information or anything that uh, moves any that cannot it cannot move with a velocity greater than the velocity of light. So the speed of light is a limit that you cannot really overcome, or you cannot so any information or anything cannot move uh, beyond this speed of light. So these are the postulates. But how it started, so or why this Einstein thought about it. So this is where the electrodynamics or Maxwell's equation plays a role. So when you go from one reference frame, so this is our reference frame S, and this is another reference frame S prime. Okay, and if this is moving at a constant velocity v in the x direction, so let's say this is our x prime, this is x. So if it is moving in x direction, so the transformation from one reference to another reference point is simply you say x equal to x minus vt. This is relative how the coordinates will change uh, in the two reference frames. Z prime will be equal to Z prime and T prime will be equal to 2. So this is known in the earlier cases, which is known as a Galilean transformation. But if you now let's write down the wave equation for potential. So del square C minus 1 by C square del square pi by del T square equal to 0. And now if you do a transformation of this equation from coordinate S to S prime, so it does not retain the same wave. It does not satisfy this wave equation. So in the frame S, this is correct, but del square phi minus 1 by C square. So del prime square, let's say I write it as del prime square del phi del prime T square is not equal to 0 in your reference frame S prime. So this was very puzzling in that time. And then people thought there must be some discrepancy either in the Galilean transformation, or there is something wrong with Maxwell's equation, or is it like there is some imaginary reference frame with respect to, so that time they call it as ether. So everything is moving with respect to ether, or at least this electromagnetic wave is moving with respect to ether, and that's why this transformation is not complete. And then there was a famous experiment by Michelson and Morley to determine this whether ether exists or not. So this is based on a interference observing or to measure the speed of light. Okay, so basically what they observe. So whatever season you do this measurement, perform the experiment, wherever you do this experiment, the speed of light always came out to be equal to c. So that experiment tells that fundamentally there is something not correct with this Galilean transformation. And this is where, in order to, and of course, the ether concept was also kind of demolished at that time. And then people came up with this Lorentz transformation. Okay, so which you can write something like, so I will write it in a matrix form, so where you can write each and individual component from using this matrix form. So this is, so if I want to write down, so so which of course you can also derive like how we reach at these relations. This is yeah, so this is, I'm writing in a matrix form. So I'm writing the coordinates, sorry, so let me do it here. So x0, x1, so x prime, x0 prime, x2 prime, x3 prime. So these are the components that that is getting uh, transform is given by gamma minus beta gamma 0 0. So beta gamma gamma 0 0 0 0 1 0 0 0 0 1. So this is a 4 by 4 matrix, and this is x1, x0, x1, x2, and x3. So these are the coordinate transformation according to your Lorentz transformation from a coordinate or a frame S. This is frame S, this is S prime. So this coordinate transformation from S to S prime can be written in this matrix form. Okay, so where, or a simple way of writing it is equal to x prime is equal to this lambda into x, where lambda is this 4 by 4 matrix. So you can write down this individual ones. So here x, what is x0? X0 is the time coordinate c into t. X1 is simply your x, x2 is y, and x3 is z. So this is how this Lorentz transformation is written in special theory of relativity. So instead of writing it as x, y, z and the fourth coordinate as ct, so you write as a 4 coordinate system x0, x1, x2, and x3, which transform according to this matrix relation. So that means what is we define here is a known as something as a space-time. So this is a space-time coordinate system. Okay. So which of course like the consequence, you have this time dilation, you have length contraction. So all these things will happen. That was described by Einstein's special theory. But what it eventually tells you that your space coordinate and time coordinate, they are not really two different coordinate systems. So they are the same or one part of a space-time coordinate system. So therefore, we are representing it with 4 vectors. So the transformation, if you want to write it properly. So what is, so I'm writing some terms here, beta and gamma. So what is beta here? So beta is just V by C, and gamma is equal to 1 minus V square by C square, square root of that, so which is equal to 1 minus beta square. So these are just simple notations that we are using. So what is V here? So V is the velocity of this reference frame, which is moving at a velocity v. Okay, so so all these special theory of relativity, of course, is one can actually, we don't see it here in our daily life, because in most of the cases our the velocity is very small, and only if the velocity reaches very close to the speed of light. So this is where we say the relativistic effect takes over. So in that case, you will see all these strange phenomenon like time dilation or shortening of time, and or the time dilation, that is the time moves slowly if the reference frame moves really fast. So similarly, the length will contract. So if the reference frame moves really fast, or you are observing the length from a reference frame which is moving at a very fast speed. But for our case, since our velocity is very small, so not speed of light, so we don't realize those effects. But this special theory of relativity and electrodynamics, so they are, so one can combine. I mean, it started with, or Einstein started with special theory of relativity, because the Maxwell's equations were not exactly the same when you do a Galilean transformation. But if you do a Lorentzian transformation, which is the basis of your coordinate transformation in special theory of relativity, so there this Maxwell's equation remains unchanged. And in order to write down those equation. So basically, you have this all these Maxwell's equation del dot B, del dot E equal to rho by epsilon naught del dot B. So all those four equations, or let's say all the four equations, or the two equations in terms of your potential. So you can write it using the notation that was developed by Einstein, and where you should be familiar with. Then so from your mathematical physics, so you should get a lot more familiar with the tensor notation. And this, what we are writing here, this transformation according to Einstein can be written something like x mu or x prime mu is equal to lambda mu and x mu. So this is again a symbol or notation that was used by Einstein. So make the things simpler, much simpler. So the coordinate transformation. So this x mu represents your x0. So mu goes from 0, 1, 2, 3. So similarly, your nu is, so sorry, this will be x nu, not mu. So now when you take, and this indicates, so you take a summation over nu. So this will be a summation over nu basically, and that will do the transformation from your one frame of reference x to the prime frame of reference x prime. So this is some of the notations that you should get familiar with. And what is the interesting thing will happen here. So if I now calculate a ds, which is similar to in 3 dimension, like we calculate dx square, dy square plus dz square. So if I calculate this kind of a space-time length, let's say, so this is a space-time length, which will be dx0 square plus dx1 square plus dx2 square plus dx3 square. And now you calculate the same thing in the transferred reference frame. Okay, so dx prime 1 square plus dx prime 2 square plus dx prime 3 square. So if you do this after the transformation, you will see this ds square is exactly equal to ds prime square. So this is known as your proper length. So similarly, Einstein defined something as a proper time. Okay, so these are some of the notations that Einstein used, and similarly, you can write down the momentum. So which, so according to Einstein now, so whatever we will write, it will be a 4 component. So it should always have a 4 component. So it is a vector, but with 4 components. So instead of calling a vector, so we call it a tensor. And then you can do this transformation from one coordinate to another coordinate frame and write all these physical terms that we have, we know in classical mechanics. So momentum, energy, which is relativistic energy, and so on. And then you can eventually write down the operators also using these transformations and write the Maxwell's equation. Okay, so I will stop here because already we are close to the time. So I will share some of, as I said, I will share some NPTEL courses online so that you can go through yourself so about electrodynamics as well as how special theory of relativity is connected to electrodynamics. So some of the lectures I will share. So you go through that and you can.
And also electromagnetic theory, sir, please.
Yes, yes. Okay.
Sir, just in 2 minutes, can you just I missed the session. I confused with the 29th day. Anyhow,
What?
so
What?
so just can you just highlight to in 2 minutes some recapping of the
Recapping, like, okay, so we started, so always when we talk about electromagnetism, electromagnetic theory and electrodynamics, so it is about uh, uh, what is the charge distribution or the current distribution and how that results into an electric field and magnetic field. So the first thing we started with in electrostatics that we have a simple stationary charge distribution and using Coulomb's law. So you can now describe what will be the electric field due to this charge distribution. So you can take it as a continuous charge distribution or discrete charge distribution that will vary the electric field. But then we could calculate. So the ultimate aim is to calculate what is the electric field due to charge distribution. So you can use different techniques. Okay, so like you can use the Gauss's law, or you can use a Laplace's equation or Poisson's equation, where you write electric field in terms of the, or write the charge distribution and the potential, and from that you find out electric field, or you take some method of images. So different techniques exist. So the same thing also exactly the same happens in case of magnetostatics, where instead of a static charge distribution, so what you have is a steady state current. So a current which does not change with time, and that will give rise to a magnetostatic field. Now you use again certain tools to calculate the magnetic field, where we used a Biot-Savart law, or you can use Ampere's law, and this is how the things are. Now the magnetic field and electric field, they will change depending on whether you are in free space or inside a material. So if I take a free space, of course, that is clear. But if it is a material, now depending on whether it is a conductor or a dielectric, so you will have some polarization. So within conductor, electric field will be zero. Within a dielectric, electric field will cause polarization that will create a new kind of vector field, that is your electric displacement vector. So similarly, the magnetic field will induce magnetic dipole moment, magnetization in the system, and that will lead to your diamagnetism, paramagnetism, and ferromagnetism. And then what we saw is like a changing magnetic field produces an electric field. So similarly, a changing magnetic field produces an electric field. So this is where we combine electrostatic and magnetostatic, and that is what Maxwell did to formulate his equations, which are very fundamental equations. And afterwards, in electrodynamics, basically what we studied is propagation of this electromagnetic wave in different medium, in free space, in dielectric medium, in conductor. So how that results into different conductivity, AC conductivity, or it changes the polarization. And then you can also cause a radiation field by changing this source itself. Okay, so the charge density and current density, they are also time dependent. So they can create a radiation field. That is what we observe normally. And that is how we can transfer electromagnetic energy from one point to another point. And then in the final section, what we did is basically to formulate, or I mean, we did not do it properly, but this Maxwell's equation actually led to a formulation of special theory of relativity. Okay, so I will share all these, some of those teaching NPTEL material video lectures, so you can go through that and learn on yourself.
sir, very
Okay,
much thanks, sir.
thank
So
you.
today just I'll look into these notations. So these are seems to be different.
Ha, ha,
So if
ha.
you not understand, then I'll.
Yes.
Thank you, sir.
Okay, thank you. So I will stop now.
Thank you.
Thank you, sir. Thank you so much.
Thank you, sir.
Thank you, sir.
Thanks a lot, sir.